Hello and welcome back. I apologize for 4.1 video. I went back and watched it, and it sounds like I'm a heavy breather on there. I don't know what's going on with the microphone. I'm sorry for that. Uh, I'm not overworking when I'm doing this or anything like that, but evidently it thought I was. So I'm trying to change it a little bit and see what I can do, and see what I can do. Hopefully it's not so bad this time, right? All right. So let me pick out pen color. I'm gonna go with red, right? Or actually, I'm gonna go with green because before I went with green. So we're in section 4.2, measuring evidence with p-values. So let's see if we can do with some p-values, and see where we can move along. So hopefully this comes out a little nicer for you. All right. So little review, quick time, right? Everybody likes a review. Giving Coke and Pepsi tastes for random people in New York City to determine if there's evidence for the claim that Pepsi preferred. We talked about this. If Pepsi is actually preferred, then Pepsi has a larger percentage, a larger following, a larger fraction, a something which is larger than 50% or 0.5, right? So what says nothing's going on? Well, this doesn't say nothing's going on because remember, it's always equality. This doesn't say nothing's going on because it's greater. It's got to be one of the two in the middle. So it comes down to the alternatives in this case. Well, in the first alternative, it says, hey, Pepsi is either less or Pepsi is greater. Because remember, this is a two-tail. Two-tail. I don't care if you're below or above 50%. I just care that you're one of the two. Well, I care because I care that Pepsi is more preferred. I have to go with letter C. Letter C is the only one which says if nothing's going on, 50% of the people like Pepsi. And if something is going on, more than 50% of the people like Pepsi. Learn to read your H sub O and your H sub A just like it's normal wording. How unusual is it to see a sample statistic as extreme? Well, now let's be careful of the word as extreme. As extreme means at least equal, if not more than. Okay? And that could be in either direction, either in a negative, less direction, or a greater positive direction. And when I'm speaking of these terms, I'm thinking of a curve, moving away from the curve. So the first bullet says, if it is very unusual, we have statistically significant evidence against the null. Statistically significant against nothing going on. Today's question, how do we measure this unusualness of a sample? If H of O is true, we'll always make this statement. If H of O is true, if the center really is the center, then what does this say about the data I have? We're going to see if this statistic provides evidence against H sub O. We need to see what kind of sample statistic we would observe just by random chance if it were true. I keep referring to this one-sidedness and two-sidedness. I've been warming you up for this, okay? So that's called pre-teaching, just to let you know. Primering, if you will. A one-sided alternative contains either a greater or a less than. A one-sided, that means a one-tail test. We practiced this already, right? Here goes the center. We found some cutoff value, and guess what? We're looking at all the stuff below, right here, less than. If it were the other direction and it were a greater than, well, I'd be looking to the other side of the curve. If it were a two-tail test, like the two-sided exam, well, then I don't care if you're below the curve, unusual. I don't care if you're above the curve, unusual. But a two-sided alternative is a not equal. Not equal, two-tail, less than greater, one tail. A randomized distribution is a collection of statistics from a sample stimulated using the null hypothesis as true. We've been doing this. This is when we went in and we did our 1,000 regenerations of bootstrapping. The randomization distribution shows what types of statistics, would be observed just by random chance if the null hypothesis were true. It says the randomized distributions will be centered at the value indicated by H of O. That's big for us. Centered at H of O. When we distribute that curve, here's H of O right here. H sub O is in the center, and all the data is hovering around there. Okay, remember, extremity happens somewhere beyond a measure of error. Okay. Key questions. How unusual is it to see this example? Okay, well, what makes it more unusual than not more unusual to see something going on? It says a randomized distribution tells us what kind of statistic we would see just by random chance if the null hypothesis were true. This makes the straightforward how to assess. When we talk about this assessment, we're talking about how extreme means from the curve, remember, from here, how far are you going away from the middle? The further you become, the more extreme you become. We need a way to quantify this evidence against the null. We got a special name for it. Ready, drum roll, the p-value. I primered you on the p-value when we were doing our distributions inside of StatKey. And when we were running a 95% test and we were finding the area of the curve on the outside edges. The p-value is the statisticalness or the measurement of area which is captured on the outside of the tails of the curve. When we talk about p-values and we look at a curve and we have a middle and we have an extremity and we have a certain number of data values, this is an area. It is known as a p-value. A p-value is the area as extreme. So then that word as extreme, it's not a singular, but it's an inequality. So in the case of what I have, my p-value is something greater than something. I am looking for the area greater than a number. It says that the p-value can be calculated as the proportion. Proportion is an area. It's going to be a decimal value of statistics in a randomized distribution that are as extreme. I can't emphasize the word as extreme enough here. This is as extreme. Here, 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 here. All of these are as extreme as what I find to be a cutoff for what is usual. And the line, remember, the one measurement of error or the two standard deviations, that's what makes something be normal. A p-value is always between 0 and 1. Your statistical p-value is always between 0 and 1. And again, it's a measurement of the proportion of the data which is as extreme as what we are looking for. So let's talk about a p-value. It says there are many ways to find a p-value. Okay, so one, we've kind of already done it in StatKey. It says if you're using StatKey to make your observation samples there, otherwise change the number sometimes on the left or on the right, depending on your H sub A, the proportion of the sample that gives you the statistic as extreme of the observed sample is observed. Okay, well, we're going to see an example of that here in a second. We're going to see that p-value change inside of some StatKey in a second, but I want to talk about it first. It says if you are given a dot plot, a randomized distribution, indicate your observed statistic and count the dots according to H sub A, sometime on the left or sometime on the right. We've done this already. We've taken a curve and we had a middle. And let's say this was our standard error and this was our standard error stop. And let's say there were 1,000 ends in here. Okay. It looks like 1,000, right? And let's say there were 2 of them over here. Well, what is the p-value or what is the chance or what is the proportion? These are all the same words that you are as extreme as this statistic. Okay, that's a stat right there. Some number, let's say it's 2.7. What is the chance? What is the likelihood? What is the p-value that you are greater than 2.7? Well, only 2 of them there are there. So 2 divided by 1,000 is equal to 0.002. I have a p-value of being as extreme or greater than 2.7 of 0.002. That's how we take a dot plot, and that's how we count or we critique the p-value. It says using the randomized distribution below to test, first of all, we have a value rho of equaling 0. So our middle statistical value is 0. And that's right here. Right down through the center is my 0. That's my null, okay? And I'm going to write that for you so you understand H sub O. Which sample statistic for R, because remember, when you go to the sample statistic to measure for the population, you're using a stat, and the stats R goes with rho. Which one of these match up with these p-values? Okay, now remember, these values here are area. These are stats. Okay, so I'm gonna map out the first stat here. Okay, so first of all, we have let's talk about an R of 0.1. Okay, so I go to the number line and I find 0.1. 0.1 is right here where I just put that red mark at, right? And I am looking to be greater. So this, first of all, you got to read some things here. This is a right tail alternative. So I need to know that. I'm going to capture all the dots on the right side. That's a lot of dots, okay? So now if I took all those dots and I tried to generate what kind of area do I think I'm talking about? Well, first of all, let's talk common sense here for a second. If I look at the middle of the data, from the middle this way is 50%, okay? From the middle this way is another 50% because all of it holds 100%. Look at the size of the red triangle. Do you think it is 0.5%? Do you think it's 15%? Or do you think it's 35%? Well, I'm absolutely going with that it's going to be 35%. And I'm using those 35% for me to judge, okay? So when I look at this value, I am going to tag R 0.1 up with a very large p-value of 0.35. Massive amounts of area have large p-values, okay? So a large value, an R of 0.1 equals a big p-value. Okay, now let's try that again. I'm going to change colors here so we can designate what I'm doing. How about we go to orange? Okay, next one. I'm going to go to the measurement of 0.3. So I'm going to go to 0.3. Notice I'm scooting over to about here. Now I'm only covering this much area here. What's my area of my yellow compared to my area of my red? Well, obviously it's less, right? It looks like it's about half as much, right? A very small amount. So now, as my area comes down or as my statistic gets further away from the middle, my p-value becomes less. As we move away from the center, as we move away from H sub O, we become more extreme and we get a smaller p-value. This is good stuff, people. My statistical spidey senses are tingling right now. I hope you got that. So the last one. By default, yeah, okay, we can just say, hey, it's the other one, but let's talk why. How come? If you don't know why, then I'm not doing my job here. So it's R 0.5. Look where 0.5 is. 0.5 is all the way out here in purple, and it's got about 5 dots in it, okay? 5 dots in it. Look how small that area is. That p-value is getting more and more significant because the data pieces in it are very uncommon. By uncommon, why uncommon? Because there's so very few of them. It is pretty extreme to be in that purple area piece over there. So for me to have a number which is, again, greater than 0.5 would have a very low percent of chance or a very small p-value. I hope this is making sense. I hope it is. Calculating a p-value. What kinds of statistics would we get just by random chance if the null hypotheses were true? That's what we were just talking about just now. Okay, what proportion of these statistics are as extreme? Remember this extreme word. How surprised am I? Well, if I go back for a second, I'm very surprised that I landed in the purple. I'm not surprised that I landed in the red. So when we talk about being significantly shocked, when we talk about is it unusual, we're talking about being in those smaller p-values. The farther out in the tail the sample the statistic is, the smaller the p-value will be. Let's commit that to our memory for the rest of the class. The smaller the p-value, the more extreme I am, or the farther I have moved away from the null hypothesis. And remember, it could be in either direction, but that last one I just did was a greater than. The alternative hypotheses, one-sided alternatives contain greater than, less than. Two-sided contain equal to. The p-value is the proportion in the tail in the direction specified by h of a. Is it a left? Is it a right? Is it a two-tail? And remember, this comes from the h sub a. For a two-sided alternative, the p-value is twice the proportion of the smaller tail. There's two tails. We'll measure that p-value, that proportion, that area, and we will multiply it by 2. So here goes a couple of nice pictures for us, okay? So it says p-values. So the first one, right tail. Notice we're only measuring those things which are as extreme. This right here is the stat that we are measuring. So looks like we are measuring things which are greater than 2, and this number is the p-value. It's the proportion calculation, and this one I think is 0.04 of red dots which are as extreme as the data given. And we can tell it's a 2 right here. Again, this is the stat. And we're measuring for things which are right tail. Go to the second one. Notice it's a left tail, red stuff on the left-hand side. Well, again, here's the p-value, much larger p-value. What does that mean? Well, that means not as extreme. It also means not as unique. There's a lot of things in that p-value because there's a lot of dots happening in there. How do you know it's a left tail? Well, look at this. It's a lesser than, which makes it a left tail. And you're lesser than what? This is the stat. The stat number is that right there. Two-tail is always going to be a double value. Two-tail, because it's a not equal. Two-tail, we are going to take this stat right here, this p-value, and we're going to multiply it times 2. 0.04, I'm just going to use 0.04, multiplied by 2 is 0.08. So the p-value here, or the proportion of data values which are as extreme, would actually be reported in 2 decimals at 0.08. Two-tail, we double the p-value. If they are different from each other on the two sides for some reason, then we will take them and we will take the larger one, and we will double up on the larger one. Gonna take one brief second here. Give me a second. All right, I'm back. I'm sorry I had to go on that little hiatus there and move about, if you will. But I was hogging up too much memory, and I had to pick it back up again. Had to get rid of some stuff. So here we are. So let's pick up where we are. So the question talks about: is it reasonably likely to occur? Is it unusual? Is it extremely unusual? Okay, so we have a couple different data values here. We're going to talk about these data values. Let me get myself organized here. When we talk about something being unusual and not being unusual, okay, remember, how extreme are we away from a data value? Okay, so let's talk about the first one. We have three different ones here. First of all, let's talk about A. A. How extreme would it be, or how shocked would you be if you had a 301? Well, okay, here's a 301 right here. Okay, right about there, right? And we're looking at things. Remember, it says H sub O is equal to 300. Okay, so our H sub O randomization distribution is 300. We're centered up at this value. Well, 300 is super close to the middle. So whether it's a right tail or a two tail, it really doesn't matter, but it is reasonably likely to occur when the null hypothesis is true. It is absolutely reasonable for this to happen. 255. So I'm going to switch. I'm going to go to a different color here. 255. 255. So now I'm at 255. Okay, well, 255. And again, we're not talking less than, we're not talking greater than. We're just simply talking about, values here, okay? 255. So I'm over here. Do you even see 255 on the scale? Answer is no. What would you say about that? I would say that that is incredibly, extremely unlikely for that to take place because it's so far from the center, I can't even find it on the chart. Extremely unlikely to occur. But don't say that it can't happen, because it can't. There could be a data plot out there we don't know about somewhere. And then the last one, 315. All right, well, 315 I see. In fact, I see 315 right here, and I see something bigger than 315 right there. So I see a couple of data values, but it's going to be pretty unusual. It is not going to be an everyday occurrence, but it could happen when the null hypothesis is true. All of these can happen when the null hypothesis is true, because remember, that's what we measure. What is the chance if the null hypothesis is true? Let's do another one. Question 14. Now we got to get some data here first and make sure we get this, and let's figure out the tailing first. Figure below shows a random distribution based on 1,000, so we know there's 1,000 pieces of data in there. We're testing for H of O, P equals 0.3, so there's the middle, versus P is less than 0.3. So right away, let's write down the note. This is the left tail. We want things that are left of center. In each case, use the distribution to decide which value is closer to the observed value. All right. So I take a look at this, and I look at the first statistic. It says for a p-value of 0.2. 0.2. So first of all, I have to locate 0.2. Here's 0.2. And if I look at 0.2, all of these data points right here are the area that comprise 0.2. Now, do I think that's closer to, and if you want to for yourself, put this into thought process, move your decimal 2 to the right, is that about 0.9%, which is less than 1%, or is the data you are seeing closer to 40%? Well, remember, from the middle to the left is 50%. So clearly, when I look at this value and I talk about this, it's clearly closer to 40%. So my value here would be, I am guessing, it's more of a p-value of 0.4. Again, I did that just using a little bit of common sense, if you will. And I looked at that and said, okay, it's closer to having 40% than it is 1% by sure. Letter B, p-value for 0.14. Okay, let's go find 0.14, which is about right here. And I'm going to color it yellow this time. So the yellow triangle indicates how much I have. Okay, the curve right there. Okay, do you think that's more like 6%? Or do you think that's more like 50%? Well, remember, we talked about from the middle to the left is 50%, and this is just an extreme tail to the left. It's getting smaller. So first of all, it's definitely got to be smaller than this one. It's got to be smaller than this because the area is comprised of a smaller value. 50% is not smaller than 40%, so we have to go with 6% or 0.06. And how about the p-value for 0.31? So let me grab another color. Let's grab a 0.31. And where the heck is 0.31? 0.31 is over here. Now remember what we're doing here. We're going from 0.31 and we're taking everything to the left-hand side, okay? We just took 50% plus more because we just took the middle and we took a little bit of the material on the right-hand side. When we do that, the answer is, are we closer to 30% or are we closer to 80%? Now, whether you think that's 80% or not, don't try to do the math here. It's more than 30%. You can't even allow that one because you took half of the curve and more. You have to go with 0.8. You have to. There's no logicalness to taking 30% on that problem. It says below the randomized distribution is 1,000 again. We're measuring this time. Look at the middle. H sub A says you're not equal. This is a two-tail. Okay? This is a two-tail test. It says the statistic for x minus 1 equals x2. Okay? And where's this thing? Why is this thing centered up at 0? Well, that's because if you took mu1 equal to mu2, and I've been doing this for you for quite some time now, and you subtracted mu2 to get it on the left-hand side, you'd be left with a right-hand side of 0. That's why we are centered up at 0. So the question is, which sample provides the strongest evidence against H of O? All right, so which one is the most extreme is what we're talking about here. All right, well, if you take the first one, and look what it says up here, x1 minus x2. So if you take x1 and you subtract x2, you get 2.2. Positive 2.2. So I would go to 2.2 positive, 2.2 about here and say, okay, this is the area that we're talking about for 2.2 positive. Then I would do the other one. I would take 94.2 and I would subtract 96.4. And guess what? I get negative 2.2. So I would go to negative 2.2. And again, I would do the same thing. Remember that curves are symmetrical. Curves are equally distributed on both sides. So when we look at these things, the right tail, even though my drawing looks skewed, the right tail p-value is equal to the left tail p-value, because remember what we do is we take a p-value, we multiply it by 2 to get the true value of a two-tail. So therefore, both problems or both provide equally strong evidence against H of O because it didn't care if you were greater than, it didn't care if you were less than. In a study conducted to investigate which method of recording phone calls or a flyer is more effective in persuading voters, since in this case the alternative hypothesis is not specified in a particular direction, the hypotheses are P of C, the call, is equal to P of F, the flyer, and then P of C is not equal to P of F. So they did a randomized distribution, PC minus PF, using 1,000. Okay, question A. If the subtraction leads us to 0.2 right here, 0.2, is it possible sample statistic? 5 possible p-values are given below. Select the most accurate p-value for the sample statistic of PC minus PF. All right, so when we do that value and we look at that area, okay, so we're looking at this sample statistic here. So we're looking at this sample value here. First of all, remember, this value is something smaller than 50%, okay? Something smaller than 50%. So if I go over and I start looking at values, the first one is 0.7%, not going to be it. The next one is 7.5%. That's pretty tight. That's pretty small. The next one is 16%. All right, well, getting closer and closer here to something. The next one is 35%. I'm liking 35%. And the next one is 80%. There's no way this is 80%. So when I'm judging the percentiles of what's going on here, I'm going to have to go with this is approximately 35% or 0.351 as given. I got that because I looked at the curve. I know half of the curve is 50%. There's quite a bit of data in that green triangle I drew, and it's probably around half of half. So it's more than 25%. So my best choice is 35%. Letter B. It says, is it this negative 0.39? So I need to find this negative 0.39 value, which is about here. And I'm looking out here to this side now. Now look, that tail just got a whole lot smaller, right? So again, now I'm going to look for the p-values. Well, first of all, there's a couple I can scratch off. There's no way that's an 80% curve. Okay. I know it's not a 35% curve because I just got done using a 35% curve. In fact, I'm not even sure that I can go with the 16% curve on letter B because it appears to me that I'm somewhere probably around a 7.5%, 8%-ish. These are getting a little tight. I understand that that it can be a little goofy to find some of these. But I think I'm going to have to go with somewhere around a 6 to 7%-ish or something like that for my p-value. So I'm going to use that 7.5% value. Of the two statistics given in Part A and Part B, which is likely to provide the strongest evidence that methods are not equally effective? Remember, the smaller the p-value, the greater the evidence. Letter B is a much stronger evidence statement against H of O because less things happened in that occurrence. When you're talking p-value, you want a very small number in order to get away from H of O. Let's talk summary, folks. The randomized distribution shows what type of statistics would be observed just by random chance if the null hypothesis were true. A p-value is the chance, the probability, the area of getting a statistic as extreme as the observed. A p-value can be calculated as a proportion. Remember, we took the number of dots and we divided by the n value, and we got that calculation for the statistic or as extreme or more. P-value is always between 0 and 1 inclusively, meaning it can be 0 and it can be 1. The smaller the p-value, the greater the evidence against H of O. It's like a reoccurring dream in my head. I just got done saying this, right? That right there is what we are trying to unlock. And once we find values of p, which are small, we have found a great amount of evidence which will, in fact, help us get rid of H of O or reject H of O.